Good morning, everyone. Welcome to the session 14 about global sorting and porosity, its effect on bed variation in time and space. I'm Mio Kasai from Hokkaido University. The first talk, or first speaker is Professor Masaharu Fujita from Disaster Prevention Research Institute, Kyoto University.
Thank you very much. And the title of my talk is about a method for estimating the porosity of sediment mixtures and the application to a bed porosity variation model. And Daizo Tsutsumi and Muhammad Suleiman, the co-author of this paper. And this is a research of the new idea of the one-dimensional bed variation model. So far, we are assuming the constant porosity of the bed material in the bed variation model, but here we are trying to calculate the change in the bed, the porosity of the bed material, as well as the bed elevation. Today, I will introduce our idea of the bed porosity variation model, but I think this model is still immature. So I'm very happy if you give me your comment and your suggestion for this bed porosity and variation models. This is the contents of my presentation. And the first, background of this research. And second is method to measure the porosity of sediment mixture. And third is bed porosity variation models. This is the main part of my presentation. And finally, I will show you some application of this model. First of all, I'd like talk about the background of my research. In Japan, the government is trying to promote the integrated sediment management for the many rivers. And there are three targets in this management. First one is sediment disaster mitigation. And the second one is sediment utilization. And also, this very important target is the conservation of river environment. From aspect of the sediment disaster mitigation, we want to make the riverbed elevation more stable, but from an aspect of the conservation of river environment, maybe active sediment transport is necessary for the good habitat condition. And also, we need to allow the appropriate bed variation. Yesterday, Professor Shea introduced the concept of the allowable bed variation range. Maybe this is a similar idea. But here, there is a contrary problem, because this is a stable riverbed. And this is the active sediment transport. There are some contrary problems here. And regarding this, just I want to ask a question to you. And I'm sorry, this is the question for the undergraduate student. Very easy question. But this is a very important point of my presentation. Does aggradation take place when fine sand is supplied to the river where the bed material don't move? That I will explain using this figure. And this is the flow direction, and this is sediment discharge. Initially, bed material don't move. That means initially sediment discharge is 0. Okay? And then we supply the fine sediment here. And maybe so sediment discharge increase from upstream side, like this. And the sediment is transported to the downstream, and the sediment discharge increasing from the upstream side to downstream side, like this. But this is the basic equation of the bed variation. This term is always negative. That means this term is always positive. That means this answer is yes, aggradation take place. But this is the example of actual river situation. This is a reservoir, and reservoir sedimentation is developing here. And in the downstream of the reservoir, maybe marine is developing, and it is a kind of sand-poor river. And the porosity of bed material changes very much. As a result, the bed degradation take place, and the deterioration of habitat is one of the big problems. Something. This situation is like this. There no sediment transport, and then so we supply this situation. And for this situation, the possible countermeasure is sediment flushing from the reservoir. Okay, we supply this sediment to the downstream. Okay, so this situation is like this. No sediment transport, and the fine sediment is supplied to here. But if we can control the sediment flushing rate, so we put a little sediment to the downstream. At that time, sediment is moving inside of the armor layer, like this. That is, there is no bed variation. The aggradation doesn't take place. Okay? And so this phenomena, so we can say the change in porosity absorbs the bed aggradation. This is a very important point of my the presentation. And before, so we assume the constant porosity in the bed variation model. We cannot analyze such a phenomena. So we need the new idea of the bed variation model. That is my point. And also, if we can predict the change in habitat conditions as well as bed variation, maybe this is a very important additional information from aspect the conservation of the river environment. What is the variables related to habitat structure that bed variation model can provide? Maybe the bed elevation is one of the very important factor of the habitat structure, and grain size distribution of bed material also is a very important factor, and sediment transport rate and grain size distribution is also very important factor of the habitat structure. And if we install the seepage flow analysis in the bed variation model, we can analyze the groundwater level change, and also we can analyze the small pond formation on the bar, something. So these are also the very important factor of the habitat. But also the porosity and void structure of the bed material is also very important factor for the habitat. But if we assume the porosity is constant, we cannot evaluate that the factor. So if we can calculate the change of the porosity, maybe that is also the very important additional information for the habitat structure. Okay, so I move on to the next topics regarding the methods to measure the porosity of sediment mixture. So far, we have several methods to detect the porosity of the sediment mixture. First one is analytical methods, and second one is water replacement method. Maybe this is the standard method. And also some people are using the frozen sediment core sampling method. And also we have the numerical packing simulation method. So here I explain these three methods. This is an example of the analytical method for two-size mixture. This is very easy analysis. And so there are two situations. This is the dense packing of coarser material, coarser particle. This is a two-size mixture, just only coarse particle and fine particles. Okay, and this is a dense packing of coarse particle, and this is a loose packing of coarse particle, and this is a relation between the porosity and the proportion of fine particle P. Okay, if P equals 0, that is no fine particles. Okay, only the coarse particle packed. Yeah, and if that porosity of the coarse particles is 0.4, the plot is around plot here, and if P equal 1, that is there are no coarse particles, only fine particles. And if that porosity is 0.4, the plot is here. And if P, when P is increasing from 0, that means the fine sediment occupies the void of the coarse particles. The porosity must be decreased like this. And also we put the coarse particle to the fine particles. So the porosity also must decrease like this. This is the minimum of porosity is like this. So this is very easy. From very easy analysis, we can get this relationship between porosity and proportion of the fine particles. Like this is very simple. And the next is the water replacement method. Basically, this method, okay, so we measure the porosity of this material, and basically we measure the bulk volume by water replacement method, and also we measure the substantial volume of this material, and then so we can get the porosity of this material. This is a standard method. But we have the technical problem in this method for armor coat. Because the armor coat, the surface is very rough, very rough. But if we remove this surface material, maybe the fine sediment appear. Okay, so this boundary will be very smooth. Okay, so looking at this two situations, that boundary profile is very different. Okay, so if we use the standard and water replacement method, maybe we lose this void of the surface. This void we lose. So to improve this method, we use the salt like this. We put the salt on the surface, and to improve this method like this. I will show you the example of the field measurement. Okay, this is a small bar, and we measure the porosity for these three locations. the grain size distribution is like this. This is a surface wet material, and this is subsurface wet material. And this is the result of the porosity for each locations. And these are for the armor layer, okay? Armor layer, and this is the porosity of the under armor layer. So you can see the just porosity is very small. Generally, we are using the porosity is 0.35 or 0.4, but in this case, the porosity is around 1.5 or to 0.25. And also, comparing these blue line and the red line, blue line is we use the salt, okay, improved method, and this is the original standard method. Maybe so you can see the if we use the salt, the porosity is getting a little bit higher than this one. But anyway, the porosity is of the armor layer is around 0.2 or 0.3 or 0.23 or something. Under the armor layer, the porosity is much smaller than the surface armor layer. That is a 0.15 around something like this. This is a result of the field measurement. And another method is numerical packing simulation model. I think in the chemical engineering field, there is some packing model. And actually, we are developing this packing method. Particularly, Dr. Daizo Tsutsumi developed this simulation model. And the flow is like this. First, we make the sediment mixture with the grain size distribution. And from this sediment mixture, we select the particle by means of a random number, and packing the particles into a hypothetical vessel one by one. And then, so we calculate the porosity. This is the flow. And I can say the packing method gives the compaction degree as a result. That is, compaction degree is depending on the simulation method. Okay, so this is developed by Dr. Daizo Tsutsumi. And first, we set vessel, okay? And next, select the particle by random number for a grain size distribution. And the first particle on the origin, and the second particle on the x-axis close to the first particle, like this. And then we find the lowest position close to two already packed particles, like this. Something. Okay, and we put the particle like this, and anyway, we find the lowest position, possible lowest position close to the two already like this. And then if there is no area, stopping the simulation, and we calculate the porosity of that material, this. Okay. And I'm sorry. So okay. So I can say this is a very dense packing because we find the lowest position of the close to two already packed particles. So that means maybe this is a very dense packing. I'll show you the result of this packing model for log normal distribution. And this is the relation between the porosity and the standard deviation of the log normal distribution. And you can see the porosity is decrease with the standard deviations like this. And for example, if standard deviation is 1.5, the distribution is like this. If this is 1 centimeter, this is 1 millimeter, and this is 1 meter. If standard deviation is 1.5, that grain size ranges from 1 millimeter to 1 meter. That case, porosity is very small. And so if the uniform part and distribution, that porosity is approaching to around 0.4, generally we are using this value. But another very interesting thing is that you know the densest porosity of the uniform particle, that is around 0.26. That is the densest porosity. Okay? But if we mix a little bit different particle, the porosity is rapidly increasing to the 0.4. That is another result. And this figure shows the cross section of the vessel. This is the around the cross section here, and this is near the bottom. These are particles, and you can find the void. Okay, and we can measure the void size. That is the habitat size. So maybe I think this is the additional very important parameter for the habitat structure. Okay, so now I want to explain the our bed variation model. This is the basic equations for the one-dimensional bed variation model. This is a continuity equation of flow and energy equation for flow, continuity equation of sediment, continuity equation of sediment with grain size dj. This. And before, so far, so we assume lambda, that the porosity is constant. So these equations are closed, we can analyze. But if so for the bed porosity variation model, we must consider the change of the porosity, this lambda. So that means we need another one more equation on the porosity. That is its governing equation of porosity. But I think this is very difficult to obtain this governing equation of the porosity. Okay, so just we are thinking about the new idea to obtain the porosity in this a set of the basic equations. Okay, this is our idea on how to estimate porosity in bed variation model. This is a standard flow of the bed variation, and we starting at the flow analysis, and then so we calculate sediment transport, and also we calculate the grain size distribution of bed material. And so here, so we are considering the mixing between the transported sediment and bed material. And also we are considering the sorting process, and also we are considering the silting process of the fine sediment, like the suspended sediment. And as a result, we obtain the grain size distribution of bed material. And also the porosity change is depending on this process. So that means there is some relation between the grain size distribution of bed material and porosity. There is some relation here. But we cannot consider the compaction degree. So, and also I cannot say what gives the compaction to the bed material. So it's very difficult. So in this model, only we are considering only these relations. And the idea is from the grain size distribution of bed material, we find out the characteristics parameter of this grain size distribution, and then so we make some relation between the porosity and these characteristic parameters of grain size distribution and getting porosity. This is our idea, and also this is the standard bed variation model, and from this one, grain size distribution, and we can obtain the porosity. But if the porosity change, also the bed elevation change, because if porosity is increased, maybe the bed level is rising up, and porosity is decreased. That means the surface level, bed level is getting down. That is depending on the change in the porosity. But so that means that if the bed elevation change, also the grain size distribution of bed material also change. So that is the implicit equations. So that is very difficult to solve directly this equation. And also we are employing the Daiso-Tsutsumi model, but it takes much time to obtain the porosity. Maybe it's difficult to, this is our method that this. Before the simulation, we make that relation between the characteristic parameter and porosity using Dr. Daiso-Tsutsumi's model. Okay, and for implicit this problem, we obtain. Firstly, we calculate the temporal bed variation and the temporal change of the grain size distribution, and also using this relation, we calculate the change of the porosity like this. Okay, and then using this relation, so we recalculate the change of the bed variation and the change of the grain size distribution and also the porosity. Sorry. Okay, so anyway, so in this simulation method, we need to identify the grain size distribution type, and also we need to obtain this relationship between the grain size distribution and porosity. Regarding the identification of the grain size type, firstly, we consider these three type grain size distribution. This is Talbot type, and this is log normal type, this is anti-Talbot type. These are typical grain size distribution of the bed material. We are considering these three grain size distribution type. And to identify these grain size distribution type, we make these two parameters, gamma and beta. And gamma is the position of D50 between the D minimum to D max. And beta is the position of the D peak between the D minimum and D max. Using these parameters, we can just identify. Okay, so I will just show you just only the result. This beta and gamma is the geometrical parameter of the grain size distribution. They're just two parameters. And for the log normal distribution, the plot the log normal distribution, the plot is around and the center, and for Talbot distribution is on this line, and the anti-Talbot distribution is on this line. And this area is Talbot area, and this is the log normal, and this is the anti-Talbot area. For example, looking at this A3 is this one. Maybe you can understand this is anti-Talbot distribution, and O3 is this one. This is a very beautiful log normal distribution. And A3 is this one. If you look at this here, this is Talbot, but you can look at this and this. Maybe you think this is no, log normal. Maybe so that this plot is around the border of the log normal and Talbot area. Anyway, so we can identify the grain size distribution type using these two parameters. And also, we need some characteristic parameter of grain size distribution type. And for log normal type, this standard deviation is just, this is the parameter for the log normal type. And the Talbot type is the D max over divided by D minimum. This is one parameter, and the other is this Talbot number. There are two parameters. Okay, so I have so much time. So just using this is the relation between porosity and these characteristic parameter, and for the log normal distribution. But anyway, so we need to a little bit to modify this relationship, and so using this one. And so finally, I want to show you some one result only. Okay, application result. There are two cases. This is case one and case two. The case one is initially bed material is Talbot distribution, and we supply the sediment little bit fine sediment. We supply little bit fine sediment. And the case two is originally bed material is log normal and no sediment supply. In that case, for example, this is the result of the simulation. Initially, the bed is covered by Talbot distribution, but gradually that the type is changing from Talbot to log normal. And in the case two is opposite. The originally log normal, but changing to the Talbot. And we can calculate the change of the porosity. Initially, this one is initial porosity, and in the simulation, the porosity is changing like this. In this case, the porosity is increasing like this. I'm sorry, so this time over. Okay, so just here I will stop here. Thank you very much.
Thanks for very interesting presentation. I quite enjoyed. But we have to move on to the next speaker. Next speaker is Professor Sekine from Department of Civil and Environmental Engineering, Waseda University, Tokyo, Japan. And the title is Gravel Sorting and Variation of Riverbeds Containing Gravel, Sand, Silt, and Clay.
Thank you, Professor Kasai, for introducing me. Good morning. My name is Masato Sekine at Waseda University in Tokyo, Japan. It's my great pleasure to make a presentation today here. I would like to introduce our new two series of experiments related to gravel transport. Two series of very fundamental experiments were conducted systematically on the process of riverbed evolution towards the dynamic equilibrium state in order to understand their each essence. Experimental set 1 was about the phenomena in upstream river reach, especially in the downstream river reach of dam, explained by Professor Fujita. And experimental set 2 was the phenomena in tidal river reach. Both two were separate, but today I would like to show you about two experimental results. Background. After dam construction, sediment supply from the upstream to downstream reach of river decreases to almost zero at some point. Under such circumstance, the riverbed may progressively undergo degradation and armoring in a river reach just downstream of bed. According to the field observation in Japanese rivers, such bed is often composed of sediment of extremely wide range of grain sizes, at least from boulder, cobble to sand or silt. Now we have to make deeper understanding of the mechanism of bed load or bed evolution change which occurred on such a bed. Here is the second one. Bed in tidal reach of river, on the other hand, is apparently different from the other reach. Mud in the clay size range flows into the reach of gravel or sandbed rivers under the influence of tidal action from the coastal area and deposit on the bed. Such bed evolution process is much more complicated than that on the bed composed of sand and gravel only. Clay riverbed is eroded by the action of water flow, and also the erosion can be affected considerably by gravel or sand transported at bed load, maybe as a result of collision or abrasion. So let's talk about the summary of two experiments. Here is a summary of experimental set 1. Model riverbed is composed of 3 groups of sediment grain sizes. Each group is represented by a single particle size. So this means the bed is composed of 3 sizes of sediment. It should be noted that each size differs from its nearest alternative size by 1 order of magnitude. One of 3 is cobble or boulder, which is the largest size of sediment and cannot move at all. It's called L particle today. And gravel is the intermediate size of sediment, and it moves as bed load. We call this M particle today. And sand or silt is the smallest size of sediment in this experiment, and it moves as suspended load. We call this S particle today. In such a bed, the hiding effect or sheltering effect of large particle on the smaller particles' movement is very important, maybe as you already know. Details about the sediment in this case are summarized in these tables. L particles, M particles, and S particles. the sediment diameters are written here. Experiment was conducted in an open channel, and movable bed is located this portion, and the erodible bed ridge was filled with sediment up to this elevation difference. I will explain you first how we prepare the initial bed. At first, we put the air particles in the depressions like this. The upper one is the plan view, and lower one is the side view. And after that, we put N particles and S particles in the void space of L particles and make a full packed bed conditions. Elevation of top of L particles is equivalent to that of N and S particles. On this riverbed, we set the constant discharge flow, water flow only, without any sediment supply. And after several tens minutes, the bed would be a static equilibrium state, something like that. In our main experiment, initial bed was said to be these conditions, and start the water flow with sediment supply. The purpose was to answer the question, how is the state of dynamic equilibrium equilibrium bed? Here you can see the experimental conditions. We investigated first the static equilibrium bed, and after that, we investigated the dynamic equilibrium state of bed. Please note that QW is a water discharge, QM and QS is a sediment supply rate of M particles or S particles, and QBE is some kind of the equilibrium bed flow transport rate evaluated in this case by Meyer-Peter and Mueller's formula. So in case 1A, we set QM is equal to QBE, and in case 1B and 1C, QM is much less than QBE. So in this case, in a dynamic equilibrium state, the top of L particles would be exposed to some extent on the bed surface. So today we mainly focus on this case. As to a second experimental set, model riverbed was composed of clay only. Clay bed had been made full compaction before experiment was started. From upstream reach of clay bed, sand or gravel was supplied onto the clay bed, and it moves. Sand moves as bedrock. In this case, we used another closed conduit was And LW bed ridge was filled with clay in these portions and sand in this portion. Sand filed in this depression could be supplied by rising the bottom plate of this portion. Details of the sediment we use in this case are written in this table. Kaolin clay and silica sand number 3 were used. Here is the experimental conditions. Flow rate of water, the supply rate of sand, and water temperatures were the parameters to change in experimental set 2. And initial bed, a water content ratio, RWC, is set to be 0.8. Here you can see the temperature in a summer season and winter season. Erosion rate of clay depends on the water temperature. So let's talk about the result of experimental set 1. Hiding effect of largest particles. In order to clarify this hiding effect, the special experiments were conducted under the condition that the bed was composed of 2 grain size sediment only. One is a LM bed experiment. Another is a LS bed experiment. No sediment was supplied in this case. This means that the bed would attain the static equilibrium state, not the dynamic one. Here you can see the static equilibrium state of LM bed, L particles, and a small dot denotes the M particles. In the right figures, you can see the some kind of static equilibrium state of LS bed. Actual shear stress exerted on the upper surface of M particles or S particles becomes equal to the critical attractive force at the static equilibrium state. So hiding function HI is defined as the ratio of the friction velocity U star E, which is actually exerted on the upper surface of each, to the average values Q star bar acting on the entire bed surface. Here is the experimental result. This figure shows the relation between the hiding function and the vertical elevation of M particles or S particle divided by the diameter of L particle dl. There are experimental data. Based on these data, we derive the empirical relation like this and was formulated by this equation. So we can estimate actual active frictional velocity or shear stress on this surface by this equation. So that's a result of a two-side sediment case. And now let's talk about the three-side case. LMS bed. First, I would like to explain about the static equilibrium state. In this state, layer of M particle only, this portion, was formed at the exposed bed surface between L particles. According to our experiment, the thickness of this layer takes almost constant values, about 1 diameter or twice the diameter dm of M particles. That is a static equilibrium state. And from this, no. And now the dynamic equilibrium bed is explained. Initial bed conditions is static equilibrium bed. I already said that. According to our experiment, it was found that the bed structure can be classified into maybe 4 stages or 5 stages in this process. Under the condition that Qm is constant below the equilibrium bed load transport rate, and if Qs is set larger and larger, the bed structure changes through the process shown in this schematic view. Please take a look at it. This is the state at stage 1. The detail of this stage will be explained later on another slide. Sorry. Stage 1, here is the supply rate of S particles, 0.2, stage 2, stage 3, and 4. Here you can see the relation between particle distance of both 2 divided by dl and qs. This is the experimental result, the data. And in this range, stage 1 and stage 3 and 4. The stage 2 is critical between stage 1 and 3. The experimental results have to quantify the before mentioned behavior based on actual measured data. So I'll explain detail about each stage. At stage 1, M particle layer still forms in the upper part of the bed here. And distance between each individual particles in this layer is not different from the one in the static equilibrium state. At stage 2, vertical distance delta S is completely equal to delta M, and at this stage, M particle layer does not appear anymore. The vertical structure in MS mixed layer is uniform. The volume ratio of M, Rm definition is written here in this layer is almost same as the value of the layer at stage 1. It's almost between 0.7 and 0.8. The porosity lambda was about 0.4. At stage 3, stage 3, vertical distance delta S is also completely equal to delta M. The upper surface approaches the top of L particles when Qs is set to a sufficiently large values. The volume ratio of MRM in this layer becomes smaller as QS increases. This means that the distance between individual M particles in this layer becomes larger than in stage 1 and 2. But the porosity lambda hardly changed from about 0.4. Another investigation was conducted also, and in this case, QM is set equal to QBE, equilibrium bed load transport. In this case, the bed surface attains the dynamic equilibrium state of stage 4, even if S particle is supplied by small amount. And in this experiment, the color of M particles supplied from upstream was changed from red to blue after the bed attained the dynamic equilibrium. MS mixed layer can be divided into two layers. One is the exchange layer, maybe a lot of blue particles here. The lower one is the deposition layer. The exchange layer becomes composed of the blue M particles and S particles, like this. MS particles in this exchange layer are continuously and repeatedly exchanged with particle transported as bed load or suspended load. But any particle in the deposition layer are not replaced by transported particles. Here is a result of thickness of exchange layer. This layer thickness becomes larger if S particle is supplied more, but it approaches a constant value of about 3 times the diameter dm of M. That is a result of set 1. And next, I will show you the result of set 2. According to our previous work, erosion rate ES, which means the volume of sediment eroded per unit time and unit area, can be estimated by these equations. And alpha here is a coefficient depending upon water temperature as well as clay mineral. We have to hurry up. And in order to confirm the validity or accuracy of these equations, direct comparison was made between them. It was seen that this formula can be reliable to predict the erosion rate of cohesive sediment only by water flow. And we also have found that wave-like undulation formed in the process of riverbed of 100% clay by sediment-free water, like this. On the other hand, such bed undulation hardly appeared when some amount of sand or gravel was contained in a bed material. So when we supply sand over a clay bed, such wave-like undulation also formed in the early stage of bed erosion. So erosion experiments of clay bed were conducted by supplying sand from upstream. We try to understand how bed elevation changed for initial 10 minutes and what the vertical structure of bed was. Here you can see 4 photographs which were taken in each case. In this case, there is no sediment supply, and more sand was supplied in this direction. As it's seen that the bed, in this case, bed surface is covered with sand and the magnitude of the undulations becomes smaller. Mixed layer thickness, delta mix, is roughly equal to the grain size DSG. DSG is a sand diameter of supplied sand. It is almost independent of the sand supply rate. Here is another 4 photographs, enlarged photograph of bed surface. Supply rate of sand was smallest in this case, and more sand supplies, and in this case, supply rate is maximum. As is seen that the area rate of fraction covered with sand increases with increasing the supply rate of sand. Mixed layer or armored layer was formed on the bed. Here is a figure of sand volume content ratio against the sediment sand supply rate. Sand supply rate increases, but there exists the upper limit and the value converges to 0.7 approximately. Here is the final figure I would like to show you today. This figure shows a relation between eroded clay volume per unit bed area divided by 10 minutes against the sand supply rate. The important point is that eroded clay volume takes the maximum values in the range around here. When QSG is less than the critical value in here, yellow portion, the effect of abrasion and collision by sand on clay erosion may be significant. The eroded volume becomes bigger. The sand promotes clay erosion early in this phenomenon more. At the same time, sand gradually deposits onto the bed surface and the mixed layer of sand and clay forms below the surface. And this layer plays a role like a bed armoring. When QS is larger than a critical range in a light blue portions, erosion volume of the clay becomes smaller. If sand is supplied sufficiently, the mixed layer forms earlier, which protects clay bed from being made more erosion. This results in the reduction of erosion volume. So, conclusion. About experimental set 1, these are the important points I would like to explain you, but the detail I have already explained. And about set 2, these are also the points, important points. Our future work will be as follows. Based on the information explained today, we are on the way to the second step. We are now developing the numerical prediction model for each event. I will explain the result hopefully at the next opportunity. My presentation is over. Thank you for your attention.